Thank you. Yeah, sorry that took a while. Next slide, please. Right. So we have a great set of speakers for you today. We have Ferdinand Sauer from Neptune. We have Michael Connor from Aztec. We have Lajko from Slush. Calvin won't be with us today, unfortunately. And we have Phil and Brandon Case from Oven Labs. The agenda this time is going to be slightly different from the previous two times. We have 4 talks today, and each talk will have is supposed to be about 20 minutes each, with 15 minutes of presentation and then 5 minutes for Q&A. And towards the end, we'll have about 10-15 minutes left for the discussion panel. Right, so let's get started. The first speaker is Ferdinand. He's the development lead on TritonVM, and he's going to talk about can machines learn with zero knowledge? A very interesting topic. Please share your screen.
Right. Yeah, thanks for the intro. Unfortunately, cool. Here come the slides. There were some technical difficulties beforehand, and yeah, somebody else will be sharing my slides for me. So I hope this will not be too much of a hiccup. All right. Yeah, cool. Thanks for being here. I work on Neptune, which is going to be a cryptocurrency, and I'm the developing lead of TritonVM, which is a zero-knowledge virtual machine. And today I will be trying to answer the question, can machines learn with zero knowledge? And the answer to the question is yes. Well, it's a little bit more nuanced than that, because can machines learn at all? Yeah, that's fortunately for you, I should say, this is not amateur philosophy hour with Ferdinand, but instead applications of ZK. So I'm just going to say, if machines can learn, they can learn with zero knowledge. And that's the part that we'll be talking about today. So first, a small preface, why machine learning, right? This is maybe not exactly what you would expect here. And the answer to that is, I currently work in a blockchain bubble, and ZKVM, zero knowledge virtual machines, they are becoming somewhat ubiquitous in this space. And that's not really a surprise. Blockchains are usually what they're being built for, and they are more or less the obvious application for them. But they can do so much more. They are a general tool. And I talk about machine learning today in an attempt for me to break out of my own bubble and maybe take you with me on that journey. Right, so here's the outline, pretty brief. First, I'm going to try and create something of a level playing field with what is a zero-knowledge virtual machine. Then we're going to talk about model evaluation, model training, a small interlude about zero-knowledge virtual machines again, and finally, model refinement. So let's get started with what is a zero-knowledge virtual machine? A virtual machine in general, or really a machine, but let's stick to virtual machines for now, is something that takes 2 inputs, input and program, and evaluates the program on the input and then gives out the output, right? That's a fairly simple concept. Now, a zero-knowledge virtual machine has attached to this piece usually a Stark prover, which you can see on the next slide. And what you will get from that thing is, thank you, is a proof as a 4th piece in this, well, it's not really a puzzle, in this diagram, right? And this proof then allows you, if you take these 4 things on the next slide allows you to prove that this for tuple of input, program, output, and proof is integral. What that means is that if you did indeed run the program on the input correctly and produce the output according to the rules of the virtual machine, then it is pretty easy to find a proof that matches these three things. But if you didn't do it honestly, then it is next to impossible to find a fourth item, the proof, such that the for tuple is integral. And you can, or anybody having access to this for tuple can verify whether or not it is integral using the verifier. And the verifier then comes back and saying, yes, this is an integral for tuple, or no, it is not. And one clue about this entire thing is, well, I guess there's two clues. A, verification is a lot faster than naive rerunning of the program on the input. And B, what this allows you, this entire machinery here, is to have secret input, which in cryptography circles we call usually the witness, right? Now suddenly this claim is a little bit different in that whoever generates the proof says, well, there is, or usually I know something, some information such that this for tuple input program output proof is integral. And that's the zero knowledge virtual machine in a nutshell. Having access to this wonderful tool, we can now see what we can do with it in the context of model evaluation. So here is how model evaluation usually works from a high vantage point, right? You have a model, you have a query, you query the model, and you get back a classification result. That could be anything. It could be, what does this picture show? And then the model says, well, it's a dog. Or maybe you're applying for a new job and your potential employers, they have a model that pre-screens all applications and says, well, do we want to take a closer look at this application at all, or do we just discard it right away? And especially in a context like the latter one here, what you want is to be treated fairly, so that if your potential future employer comes back to you saying, sorry, our model has said you're not a good fit, then you would like to know that they did indeed run this model in a fair manner and did not apply one model to you and a completely different model to another applicant. And that's where zero knowledge virtual machines can come in. Because if they do supply such a proof to you, then you know that you've been treated the same way as everybody else. That's already pretty cool. Now, a pretty big downside of this is, in order for them to prove this fact to you, they have to reveal their model. And that's not usually something people want to do. But zero knowledge virtual machines got your back. Because there is a neat trick here in that you can hide the program, which in this case is the model, by using the secret input or the witness. And on the next slide, you can see a rather high level look at how this can be done. For example, you take the actual model, scramble it up by throwing it into a hashing algorithm, and then only use the digest as the program, right? And the actual program is being fed in through the witness. And this is a very high level look at it. If you want to take a closer, if you want to more completely understand how this thing called program attestation can be done, take a look at Bobin's Threadbare's presentation from last month's panel, where he talked about at least 4 different ways to do bootstrapping, which then results in program attestation. Right, and now you can hide the model, but still prove that you treated everybody fairly. That's already pretty nice, but it doesn't solve the problem that if your model is biased, then you will treat people unfairly anyway. Maybe you trained it to do such a thing, right? So let's take a look at model training. Well, here's what model training looks like from a very high vantage point. For that, yes, thank you. That's the same thing again, right? I'm very lazy in creating my figures. You have, no, sorry, Ibrahim, that is correct. I wanted to make a point. From a high vantage point, it looks like the same thing we have seen twice so far already. You have a learning algorithm, which is just a program. You have some data, which is the input to that thing, and what you get is the model. So first up, what you can do is, if the data were still the public input, then what you can do with a zero-knowledge virtual machine is you prove that the learning algorithm was applied correctly. I think it is a pretty fair assumption to say that the learning algorithm is public most of the time anyway, due to academic literature. For example, backpropagation is not a secret. And all the other ways to do machine learning, they're not secret either. Well, probably some of them are, right? But I think it's a fair assumption to say that most of them are not. Right, so if you have the proof, you can prove that you trained your model according to the data correctly and did not introduce bias willy-nilly. All the bias has already been in the data, or maybe your learning algorithm is good, right? But you probably don't want to publish your data. Or maybe you do, maybe you don't. But if you don't, then there is a very straightforward way to not do it, in that you just use the interface for the secret input, i.e., you use the data as a witness. The next kind of not so nice thing about this is that you're leaking the model. So what can we do to prevent that? Well, here's a quick fix. We apply the learning algorithm, and then after it is done, we simply throw the result into a hashing algorithm, scramble the thing up, and the real output is the digest of the model. And now if you want to prove the integrity of the entire thing, whoever you prove it to does not get access to your model. They only see the hash digest of your model. So they can't use your model. But you can't also. Where's the model now? Well, here's a cheeky trick to get something like secret output, because our current interface does not have that. But you as the prover, you have full control over the virtual machine. So what you can do is at the right point in time, namely just after the learning algorithm has finished and just before the hashing algorithm starts, you take a peek into the virtual machine and you take notes. You say, what do we have here? Well, that looks like a fully trained model. So you just copy that over to your hard drive and bam, you have secret output. And that should be visible on the next slide. And this is a kind of, it's not per se in the interface of zero-knowledge virtual machines, but it's a cool trick that you can do. And now what you have is a model that you did not reveal, but that you published the hash digest to. So now you can do program attestation when you evaluate this model, which was the previous concept that we looked at. Right, those are two rather cool things, I should say. Let's take zero-knowledge virtual machines to the next level by bringing in recursion. For that, we do need the two next slides. Thank you. This is a figure that we've seen before, right? This is the interface of a zero-knowledge virtual machine. Now, the figure is set up in a way, and I've described it before to you in a way that should make the next step seem rather obvious, in that the verifier, that's a program. The verifier takes its input, whatever the for tuple was beforehand, right? Input program, output proof. And it produces an output, namely its verdict. So by connecting these things down, we have achieved recursion. And the recursion, the statement of the recursion is we have computational integrity of a computational integrity claim. And if you go to the next slide, right, if we just set these things to be equal, then that's maybe interesting for academic purposes. But if we, like on the next slide, use them as part of something bigger, say a bigger program that takes more input and produces more output, now it starts becoming really interesting. And this is something that we can use for model refinement. For example, for model refinement, right? Say you have a model that works, and now you have more data. You maybe don't want to train a new model using your old data and the new data to get a new model, but you want to reuse the model that you already have and just add the new data to it. And that's model refinement. And you can use recursion to do this in a provably correct way. If you have a proof that your old model was trained correctly, then you can use the verifier as part of your program, as seen on the next slide, to create to attest to the correctness of model. And then you have a new model that is, you can also easily prove that it is correct without having to rerun the entire training from scratch. And this is one way to use recursion. Another way to use recursion is by batch verifying, or in the machine learning context, for example, you can use federated learning. You have multiple machines that each do their own thing. If you could go to the next slide. Thank you. Then you have a bunch of models that come back to you, and you combine them all into your one big model. And here you can do basically the same thing, right? You get 3 proofs associated with the 3 models, run the verifier 3 times on all of those 3 proofs, and get a model for which you, and get a proof for the combined model. One more, please. Thank you. Right. And yeah, that way you can reduce recursion in 2 different ways to achieve 2 different goals in the machine learning world. And I think that was all I wanted to talk about today. Just a quick summary on the next slide. What have we talked about? Zero-knowledge virtual machines. Using them, you can combine zero-knowledge and non-zero-knowledge techniques of training or evaluation, or you name it, in the machine learning world. And more concretely, the next bullet point lists what are the things that you can hide. Namely, you can hide your training data, you can hide your model, you can hide the classification result, any combination of the above. And if you hide everything, then you probably don't want to run a ZKVM, but just a laptop in a basement. That's it from me. Thank you very much.
Thank you. Thank you. That was very, very nice. We have some questions lined up for you already. There was a question in the Zoom chat from Thomas. He's asking if the input is always required for verifier, and if the verifier by definition is working outside of ZKVM.
So the input that is not the secret input, yes, that is the required for the verifier. But if you don't want to reveal a certain thing, you can just use it as the witness or the secret input. And the other question is, the verifier by definition always working outside of the VM? No. As we've seen with recursion, you can just run it in the VM and then you get really cool properties. But it does make sense to stop this recursion at some point and have a verifier that lives outside of the VM. Yeah, so probably you want both.
Right. The next question we have here is from Nicholas. He has a couple of questions actually. The first one is, with recursion at every step of the way, how big do you see the overhead of verifiability, and is it feasible? The second question is, would the proofs be geared towards ensuring the learning is verified from the builder perspective, or could end users benefit from it by verifying that maybe an ML model learned via the right data? I hope I'm reading it right there.
Right. With respect to the first question with which talks about overhead, actually, I do not currently know the overhead that would be implied when you do this with a zero-knowledge virtual machine. This is, as I said, this is more a me breaking out of my bubble thing than me actually doing this thing. So I don't exactly know how much slower things will be. But I can imagine that if people really want this, then you can make this really fast. And why do I think that? Well, first of all, this entire technology with zero-knowledge virtual machines is just beginning. Within the next few years, I believe that we will see tremendous speedups. And two, once hardware starts being part of the mix, things will step up to the next level. We have seen this with machine learning. Once people have started to produce hardware that was dedicated to training, they could train much bigger models. And with respect to zero-knowledge virtual machines or not, zero-knowledge tech, the hardware is just, I don't think it has started yet. I think people are considering starting hardware accelerators for this. And there's no reason not to combine the two. So for now, I'm assuming the overhead is large, but it doesn't have to always be. That's my assessment, or my opinion currently, I should say.
So I'm sorry, but I'll have to stop you here.
Oh, sorry for answering so few questions then.
There are many more questions actually, and one person just sent me a list of 6 questions. So people definitely are very curious, but we'll move on to the next talk.
Feel free to ping me on other channels. Thank you.
Sure, thank you. Yeah, great talk. Thank you so much. The next talk is by Michael Connor. He's a cryptography engineering lead at Aztec, and he'll talk about the potential of private smart contracts.
Hello, thank you. Let me try and share my screen. Okay, let me minimize all this stuff as well. Can you see my screen?
Yes.
Super. Yes, so I'm going to talk about really high level how we at Aztec are going about designing a private smart contract platform. And I will start with the kind of history of where we've been and how we've got to this point, and then talk about our ideas going forward for private smart contracts. So in the beginning, there was Ethereum. So with Ethereum today, you can execute all sorts of different functions on different smart contracts, DeFi, gaming, all sorts of things that I guess everyone on this call is familiar with. But I guess there was one problem that's different from how society kind of transacts financially in the traditional finance world, is that all information is public. So inputs to computations are the computations themselves, and the state variables which get stored, they're all public for everyone to see. And for some use cases, for many use cases, for regular people and for companies, that's possibly not acceptable, and they would prefer privacy. Another secondary point for us is that it's also quite expensive, depending on whether you're in a bull or bear market, to transact on Ethereum. So we've seen a lot of people build rollups to bring down that cost, and we at Aztec are no different. So a few years back, our first iteration of bringing privacy to Ethereum was the first version of ZK money. And what that made private was just the transfer function of an ERC20 contract. And an ERC20 contract is just fungible tokens, if you like. But I guess there was a problem with that, is it was still on layer 1, and layer 1 was very expensive. And the way we hid things was through a ZK snark circuit, proving that you have permission to transfer funds and then transferring them in a Zcash-like way, and I'll talk about that soon. But verifying that zero knowledge proof on chain cost hundreds of thousands of gas, which is lots and lots of dollars. So we had private money, but still everything else was public, and all these other use cases were not available in private, and still expensive, as I said. So then we move on to the next incarnation of Aztec. Our first layer 2, if you like, where we still only did the transfer function of an ERC20 token in private. So you could still only transfer value from one person to another privately without people learning who you are or what the value is you've transferred. But this time you could batch it with lots of other users. So you're amortizing the cost of that verification on chain across lots of people using a ZK rollup, which is, you know, there's loads of them out there now, and most people are pretty well versed in how those work. So we had cheap private money, but everything else was public. And for those maybe not familiar with rollups, here's a little pretty picture. So we've got all these transfers happening at the bottom. They generate zero knowledge proofs of the correctness of the rules of transferring funds, you know, not creating or losing value, all that good stuff, proving that you have the secret key, blah, blah, blah. And then you send it to a rollup provider, and they verify each of those proofs and themselves generate a zero knowledge proof of the correctness. And then you move up to the next layer, you verify the zero knowledge proofs below and generate a zero knowledge proof of the correctness, all the way up until you're left with one zero knowledge proof that you can verify on chain. And so rather than doing n verifications, you end up doing one, and it's way cheaper. Yeah, one verification is cheap. And these are, I guess, yeah, the ZK rollup maybe is arguably a misnomer for a lot of rollups, because a lot of rollups don't actually hide the data or the information being rolled up. But at Aztec, because privacy is our mission statement, we do the extra computational steps in order to generate a ZK snark and actually hide the data that people want to be private. Okay. Okay, so the next incarnation of Aztec, we went a little bit further, and this is our most recent release called Aztec Connect, which we released about a month ago to Ethereum. This time we added two new functions, the ability to do a DeFi deposit and something called a DeFi claim. And you can see at the top here, this unlocked the ability to interact with not just an ERC20 token functionality, but interact with lots of other DeFi smart contracts on Ethereum. How does that work? Well, let's look at that in a bit more detail. So already we had an established pool of private tokens in Aztec. So private money, each of these envelopes represents some money owned by some person. And on Ethereum, we have all these different DeFi contracts, and it might be a swap contract, but you can do lending, borrowing, staking, and we're slowly adding functionality over time with different partners. All people have to do is deploy about 100 lines of code, create this thing called a bridge contract, which is a very standardized interface. And that enables users to send money to layer 1 from this private pool, swap it, or do some other DeFi interaction. And most DeFi interactions end up giving you tokens back. And then you can shield those tokens again in our pool. And observers from the outside don't know who did that DeFi interaction. So users retain anonymity, but people see the values being transacted. But that's an okay level of privacy for some use cases. What's more, if lots of people want to interact with a particular DeFi contract at the same time, we can batch all those deposits together and we amortize costs that way on layer 1. But I guess there is a but, even though that's a really cool use case and we're really proud of it. Layer 1 inputs are still public. Layer 1 states that get stored in persistent storage on all of these different DeFi contracts are still public. Computations are still public, at least the ones which happen on layer 1 are. And the layer 1 contracts that people interact with is still public. So our mission now is to make all those things private to allow an explosion of different use cases, and to start bringing all of the things that we can do with traditional finance, all of the privacy we enjoy in the normal world, bring that to the blockchain. Here's just a reminder of the previous slide. And there's still only one private state type in this whole model of Aztec Connect, the person's balance. So a big goal of the next iteration will be to make more states, unlimited state variables. Okay, so this is what the next iteration looks like in lovely pictorial form. We've got Ethereum up at the top, as it was before, and we can copy what all of the other rollups do. We can have functionality of any smart contract on our layer 2. With public functions and public states, and implement different versions of existing smart contracts on the layer 2. But also what we're planning on doing, and this is the crux of Aztec, is we will be allowing people to deploy private functions to their smart contracts and store private state. And this will unlock use cases which aren't available on traditional blockchains or layer 2s, which is really cool. What do I mean when I say private state? Well, on Aztec Connect today, we just have values. You've got an asset ID, a value, the owner of that state, and some salt to keep it private. And we hash it with a Pedersen commitment, and that hides the value from observers. Well, to generalize that, we can just do this. We can add a contract address, a place where you can silo the state variables of a particular contract. And we can add a generic storage slot instead of an asset ID to allow you to label any state variables in much the same way as there are storage slots in Ethereum. And the other values are the same. And instead, we just put them in our cryptographic envelope or commitment. And here's a bit of background on how Zcash kind of functionality works. So we pass as an input to our function our hidden state that we just talked about. We prove that it exists somewhere in the tree of private states. And this is all happening within a ZK Snark circuit, which we allow developers to build with our Noir language. And within the circuit, you open that commitment. You might reveal that you know the contents of the commitment, and you might prove knowledge of the owner of the commitment in order to validate that you're allowed to edit the state. You generate what's called a nullifier based on a secret only you know. And then you perform a computation on the value of that commitment. And then after you've finished computing stuff and you want to store that variable persistently after the computation, you just wrap it in a new envelope, add a different kind of randomness. You might change the owner, you might change the value. And you store the nullifier in the tree to prevent that note from being changed in future. And you store the commitment in the commitment tree in the next available leaf. So it's a very simple protocol. And we can use this for just generic state changes of generic, what we're calling private smart contracts. So that's all it is. That's all private state means in what we're planning to build. And this obviously has to happen on the user's device. So that's quite different from current rollups and current blockchains, where all computation is done by the leader of that block or the rollup sequencer. This has to happen on the user's device because these are private inputs being handled, and we don't want them to get leaked to other people. So we end up with, okay, I'll talk about that in a second. And we also want composability. So at the moment, most ZK apps that are deployed to blockchains are kind of individual circuits that don't interact. Whereas functions on Ethereum, you can have functions calling functions, calling functions, calling functions of all different smart contracts, which is really powerful and really useful. and allows so many more use cases. So in order to do that with circuits, we need something called a validation circuit, or you might choose a different name, where it checks the rules of if you have a circuit that wants to call another circuit and pass inputs to it, the validation circuit checks that you are adhering to all of the rules of this smart contract platform that we're building. And this is turning into quite a complicated circuit. But what you do is you have recursion. So if you have functions calling functions, calling functions, calling functions, you just recurse each of those through this validation circuit. So we have a high amount of recursion, and we're designing and improving zero knowledge proofs in order to achieve this on our roadmap, which is really cool. Oops. Huh. There you go, recursion mean. Okay, so we end up with 3 layers rather than like layer 1 and layer 2. We have kind of layer 1, public layer 2, and private layer 2. The reason we have the 2 different layers in layer 2 is some computation has to happen on a user's device. All of the private function execution and private state changes, we don't want them to leave a user's device. So our client is split into 2. And therefore, when designing smart contracts and using the Noir language, we'll need to warn users that you can't necessarily make particular calls. You can't call from public to private very easily because there's this arrow of time. You do the private computations first and all those functions get executed in your call stack. And then you move on to public computation. And this has to happen, this has to be done by one party because they need to choose the order in which particular states are edited. You don't want people colliding and changing the same state at once in much the same way as all other blockchains. And then eventually you can interact with layer 1. So you've got these 3 stages of computation, and all of this is just snarks being recursed and passed to different people all the way up to the top. How do we abstract all of this complexity from developers? Well, I've mentioned Noir language, so that we're releasing another iteration of Noir in the coming months, maybe weeks, which is an improvement on the previous version. We're building layer 2 clients, both public and private, to try and achieve all of this complexity, all of this handling of zero knowledge proofs and abstracting it all away, and all sorts of great tooling. So we're trying to build all of the great tooling you enjoy with Ethereum, but also with the added complexity of managing private state and private function execution and not leaking information. And we're hiring. Yeah. So if that sounds interesting, I guess our job boards are on AngelList or Greenhouse, or get in touch on Twitter. And yeah, that's the talk. Thank you.
Excellent. Thank you. Very nice talk. And we have a few questions for you already. The first question is from Nick. It's in the chat. Is the pool of assets shown the equivalent of a multi-asset shielded pool?
Yes. It's a pool of many different types of assets that are all shielded. Yeah. So I guess you could say it's a multi-asset shielded pool. Yeah.
How heavy is the math or cryptography employed to make it possible? Could it be useful outside of the concept of money?
The maths is very complicated, very heavy. We're squeezing every last drop out of what we can do with ZK snarks, and cleverer cryptographers than me are coming up with cool improvements on our existing snarks. Could it be useful outside the concept of money? Yes. So ZK apps, they don't have to be, as smart contracts on Ethereum, they don't have to be money. They can be games, they can be other things. A smart contract is just a set of rules that you are forced to adhere to. So those rules could be anything. They don't have to be money. Yeah.
Right. Jim has a question. He's asking if the transition state changes, can you speak to the transition state changes and how they are communicated from the nullifier leaf?
That's quite a complicated one, and I know we're short of time. I think Zcash documentation explains this the best if you're new to the subject. So I'd recommend checking that out. But a nullifier essentially is a clever way of preventing someone changing the same, double spending a state change, if you like, but without revealing which state has been changed.
Right. Any other questions? Let me see if there's any question in the Telegram group. Okay, I have a question, by the way. So you mentioned anonymity somewhat briefly, and you know that there are different types and levels of anonymity. Sometimes it could be everyone who participates is part of your anonymity set. Sometimes you have to choose how big your anonymity set has to be. And sometimes anonymity might also depend on how actively the system is being used. So if a lot of people are using the system at, around the same time as you get good anonymity, otherwise you don't, right? So I'm wondering what kind of anonymity do you provide with Aztec?
With Aztec Connect at the moment, all transactions, all transfers look the same. So you get the complete anonymity set if you're doing an internal transfer. If you are doing a DeFi deposit, you still get anonymity because no one knows who is sending money to the DeFi layer 1 contracts, but you do lose, I guess people can see the values being moved, but that's okay if people don't know who you are. It's kind of similar to a VPN. But you're right, when people deposit and withdraw from the system, if there are noticeable patterns, if someone deposits $1 million and then 5 minutes later $1 million is withdrawn, there's obviously ways things can leak. So there are ways people can do statistical analysis on this stuff. And I guess that's something that the whole industry can work on analyzing and figuring out best user practices.
Cool. Thank you. And I think we might have time for one more question. There's a question from Tom. Is there capacity for compliance or auditability to avoid regulatory friction like Tornado Cash?
So yeah, we're aware of the Tornado Cash situation and developments this week. I think Aztec are releasing a statement next week. So I'll let that statement do more justice and a better explanation of all that subject than I can do here. Yeah.
Cool. Yeah. Thank you. Great talk and for answering all those questions.
Thanks very much.
Next up, we have Ago, who's a co-founder of Slush SDK, and he's going to talk about ZK rollups for app-specific scaling.
Hey, everyone. And yeah, thanks for coming to this presentation. Let me share my screen. Okay, great. I assume people can see this. Cool. So I'll be talking about Slush and the Slush SDK. And the way I framed this presentation today is to walk you through our thought process and like how we arrived at building this specific SDK and what we've been working on previously. So, okay. So we started off by reading this article from the Starkware team, which talked about fractal scaling. And there's always been a question of like how much scale will Ethereum need? And in this sense, perhaps my talk is falls into the natural category of like using ZK tech for scaling. So there's been this question of how much scale will Ethereum need, and also besides the processing power, where will the data be stored? And this is an image that kind of illustrates perhaps what this will look like in the future with Ethereum hosting a number of different virtual machines. So the core takeaway from this image is that each of these squares or semi-squares has its own virtual machine and may have its own data availability solution as well as decentralization. So originally, what really excited us is how we can really push this scaling to its edge. So in a way, how we can have linear scaling with a number of nodes. And the way we started asking this question is, okay, if we have validiums where all the data is only accessible to the specific validium, then it's not clear how you can make this whole system secure. That is to say that perhaps if you're a layer 3 within this network and you store your data and the layer 2 above you also stores its own data, then what happens if that layer 2 becomes untrustable? And basically, there are some potential solutions with tools that kind of resemble data availability committees, where each Validium can store its own data. And in case where one of these becomes untrustable, we can get rid of that virtual machine and replace it with one that actually can take its place. And in this sense, if we have this fractal tree that where each Validium stores its own state and its own data, then we're turning this like data availability on its head, where all the data is not really concentrated on L1 on Ethereum, but it's much more spread out, much more homogeneous. So we're thinking along these lines of how the scaling is going to look like in the long run, and then we're of course also think about like what part of this process can we actually build right now. And this is what we effectively are doing now with the /SDK. And our core insight here is that app-specific rollups will be very important. And to illustrate this, here's a tweet by Max Gillet. If you don't yet follow him, then I think you'll be better off. He is building a Stark prover, and his idea that like well encapsulates our stance, and what we've been thinking about is that there will be a load of virtual machines with provers, and these will be semi-independent. So the road that we see ahead is that effectively we'll have a number of L2s, and all of these L2s will be hosting L3s, and some of these L3s will be app specific, in the sense that it's going to be a single virtual machine running a single app, where the app has some amount or full control over what is being run on that virtual machine. Of course, this this bumps into a problem of communication between the different app rollups. So we see three trade-offs here, basically. And these trade-offs lie along the axes of computational resources, the amount of decentralization, and also data availability. And like three use cases that are interesting here is, for example, building an order book where you need a large amount of computational power, where you really just want to have the best prover available, and you don't necessarily care about how decentralized this platform it is, and you'll be storing low amounts of data anyway. And a second use case that we have seen is you want to build some decentralized platform that doesn't run afoul of regulations and helps you put a number of apps on different chains. And here, what is crucial is to have it decentralized. And lastly, if you want to run a game or some NFT, like some app that uses a lot of NFTs, data availability will be like super cheap data availability will be crucial for you. So to speak concretely of the /SDK, what we're building here is an open source SDK that will allow you to spin up L3s on demand. What we're initially starting off with is implementing the Tendermint consensus mechanism to work on StarkNet, meaning that our starting L3s will be decentralized Tendermint nodes on StarkNet. And here the crucial problems are with building a light client that runs on the StarkNet virtual machine that is able to read Tendermint, and also adapting Tendermint to work with Stark signatures. So I previously alluded to this problem of being able to communicate between a number of virtual machines that lie, how a large number of nodes that have their own virtual machines. And the solution that we see here is to implement a trustless bridging mechanism. So let me just go through with you this technical slide here. So in this case, L1 is just Ethereum. There are a number of L2s, and then there are a number of L3s within a specific L2. And what you want to do is you make some transaction on this L3 that has the identifier 3 here. So you make a transaction there, and you want to basically be able to prove or to show that this transaction happened. And you want to be able to do this either on any of the L2s or any of the L3s here. So what you can do is you can take the Merkle root that belongs to this specific transaction. So either this is a storage variable change, or if it does not affect the storage variable, then there will be some hash, and it will be a transaction that is also stored in the Merkle tree. And so you can take this Merkle root and pass it along to the other virtual machine where you want to prove this. So on this independent virtual machine, oh yes, this passing along happens off-chain by specifically taking out the Merkle branch from the full nodes database. So on this node where you're passing it to, there will have to be a smart contract that implements the hashing algorithm. And if there is such a smart contract, then you pass this Merkle tree to the smart contract, then you'll be able to prove that this transaction actually took place on the independent node. So here you're comparing the hash of this Merkle branch to some state change that was passed from this L3 down to the L2 and then down to the L1, and then was passed up to this L2, meaning that we're comparing this this hash to the state root of the third virtual machine. And what we see is doing this trustless bridging will allow a lot of Ethereum-based and like Merkle tree implementing rollups to communicate with each other, and to get around the fact that there will be like a number of app-specific rollups that are semi-independent. So we're currently working on and looking for people to join us on this journey is building the Tendermint implementation of an L3 on StarkNet, and also building a simple command line interface for this. Thank you for listening, and there are 3 channels to follow us on Twitter if you want to take a note, and looking forward to questions.
Thank you. Very nice talk. Do we have questions for Lajko? You can post the questions on Zoom or on the Telegram group.
So yeah, can data remain private while on L3? Nicholas is asking. Yes. So this this depends on how you basically configure the L3. So there will be options to keep it private. And if you are in control of the L3, then, and you're the only app that's running on that specific L3, then yes.
Maybe I can ask a question. Okay, there is another question. It's on the Zoom channel. Data storage and data availability are 2 distinct concepts. While you can use the L3 Tendermint chain for data storage, how do you prove to the L2 that the data has been made available by Tendermint?
Yeah. So yeah, Kalman is the person. So there's 2 of us building this, and Kalman is working on this, and he's the one I will forward you to, Francesco.
Another question, can you talk a bit more about L3 speed aspect? This seems to be a bottleneck or constraint to me. Any comment?
There's again this trade-off with L3s that exists with L1s. So for example, Solana is to some extent much faster because they are much less decentralized and have hence much larger nodes that are effectively servers. So there'll be this trade-off of, if you want to have an L3 that is just a Validium and you're the only one running it, then you can make it very fast and can put a prover behind it that's also very fast. If you want to have it decentralized, then that will be a different topic, and there you'll have to run some consensus mechanism that will also slow it down, and it will be more expensive as well. Yes.
Right. Any other questions for the speaker? Okay. I guess we don't have. Thank you again, Lajko. Great talk. And now we have the last talk for the session. The speakers are Phil Kelly and Brandon Kase. Phil is the head of BD at Owen Labs, and Brandon is an architect engineer at Owen Labs. And they're going to talk about innovations in zero knowledge proof applications.
Cool. Thank you very much. Great. So thanks for having us, Delendam. Thanks for running this series. It's really, really valuable. So we're from the O1 Labs team, the team that incubated the Mina protocol. You probably know that Mina blockchain launched around a year ago now. And we've been working hard since then on a number of things. One of the things that we did was have the formal launch of our framework back in June to allow people to build ZK circuits. It's called Snarky.js. It's based on a Plonk proving system, which we developed called Kimchi, that's been open sourced. A number of things that we like about it. Number one, it doesn't require trusted setup. It does contain infinite recursiveness functions, and then a number of other components that really just help to optimize it as a client-side proof generation system that you can run in the browser efficiently, and then send proofs to Mina for verification and storage and state storage. So that's part of a unified system. You probably know from Mina's launch that it's a very succinct blockchain. The state root is under 22 kilobytes. And one of the other things that's been happening since Mina was launched is that the Mina Foundation and the Ethereum Foundation have been working on a bridge with a company called NIL. So the NIL bridge is already in demo, and that will allow the whole of the Mina state root to be stored inside a smart contract on the Ethereum mainnet. So we've got this ecosystem. We've got the system for writing ZK smart contracts, ZK circuits, which is Snarky.js. They get verified on Mina. And then we have one bridge already, with a lot of progress towards storing Mina state root on Ethereum mainnet. We are going to talk today about two things. First of all, I'm Phil Kelly, I'm on the BD side. I'm going to do a quick run through some market use cases and what we see as the emerging use of ZKPs in the market. And then Brandon, who is one of our
Hello.
Hi. Can you hear him?
Yeah, sorry, I was just saying hello. I'm Brandon.
Oh,
so keep going, Phil.
Is going to talk about a use case involving a game and use of the recursive functionality. So very quickly then, just some quick framing of this. There's a ton of interest in ZKPs, but obviously it's really early days in the market out there still. The good news is that there's a ton of work going on. So we've got various groups looking at use cases and developing primitives. I don't know whether anybody saw Vitalik's presentation from ETH Seoul last week. He did a half hour, which was, basically all talking about use cases. So that's a great watch if you haven't seen that already. The themes that we're seeing, I think kind of roughly fall into three areas: privacy and attestation, dApp-specific rollups, and oracles, but you could probably add bridges to that list as well. It's just there's further to go, I think, on working out exactly what the right bridge use cases are. There is lots of focus on solving Web3 problems. In fact, I think that, I mean, obviously Web3 has been the driver of a lot of the new developments in the technology, and that's probably where it will first get used, but we think there's a ton of use cases in the Web2 world as well. And then finally, just some indications of companies that are starting to work with us on Snarky.js and building ZK smart contracts. When we launched back in June, we recruited 8 partners who are going to put Snarky.js through its paces, test it a bit, and give us some feedback to help us refine our roadmap and smooth out any road bumps there. Also hope that some of them will go through to live production, but still working on some of the early work there. The work they're doing is obviously confidential, but you can see some of the names there. And it's a nice range of names across various segments of the market. So we've got Brave Browser, Dia Data, which is an Oracle provider, a couple of identity providers there, Snickerdoodle and Sysmo, Parcel and SmoothSwap are in the DeFi space, and then ETHSign obviously is for secure document management. So a very brief run through some of the areas of the market that we think will be ripe for adopting ZKPs. First one, very obviously, and A is the area where most of the ZKP adoption has actually taken place over recent years. Private transactions exists at the protocol level and also at the dApp level in the form of mixers. Obviously, tough week to be talking about this, but does lead us to the question as to whether there will be now an evolution of some of the mixer protocols to incorporate either some kind of gating, which is common sense restriction of access to the pools, or even fully OFAC screened and fully KYC'd access. Obviously the challenge there is that it reduces pool sizes and transaction numbers, so it makes it easier to track coins in and out of the mixer, even without specific knowledge of the path. But as use of private transactions grows, that could be viable. Identity, second key use case, and again, somewhere where we've seen activity starting already. There's a lot of new startups, as you all know, in the identity space, and some really interesting conversations going on. There's at least 4 headings. Identity is a surprisingly complex space when you get into it. There's at least 4 facets to it that I've listed out here. One is simply, one-on-one anchoring of a real-world identity to a Web3 presence. That's the kind of thing that Proof of Humanity is trying to do. It's kind of at least loosely linked to the idea of soul-bound tokens. There is the addition of verified credentials to identity to enrich them, and obviously, as much as possible, people would like to do that in a way that doesn't completely dox the underlying information. Hence the use of ZKPs. It can be achieved either with non-transferable NFTs on-chain or with off-chain proofs. So again, a big debate going on about that in some areas of the market at the moment as to what the best approach is. And the actual use cases there span everything from social to attesting to your experience. When we have delegates for DAO voting, it'd be nice if the delegates could tell the community how much experience they've got and why they would be a good delegate without having to reveal all of their wallets and all of their Web3 activity in supporting that. Credit, we worked on a credit use case last year, allowing a user to bring their exact credit score into a ZKP and output from that a range, just to help to generalize and preserve some privacy in using Web2 credit on-chain, which obviously could be a great way to expand the use of DeFi and enrich it. And finally, just general reputation. Third area, kind of building off that, I mean, people are increasingly having extremely complex and fragmented Web3 lives across multiple chains, multiple wallets. It would be nice to be able to aggregate that without having a single honeypot of data. And ZKPs could be used to do that, getting underlying information on wallets and transactions, putting them through ZK smart contracts, and then pulling together an overall picture for a user. And then finally, turning all of that around. I mean, most of what we talked about there is increasing identity, but turning all of that around, you can have identity that you then re-anonymize and allow anonymous activity on or off chain. Building on that, I mean, we're already starting to see some use cases on exactly that theme. So proving that you're part of a group to allow you to get then anonymous access to something. So that could be private voting, anonymous voting. It could be access to a communication channel. I think there's a couple of examples out there already where if you can prove something, you can have access to a shared Twitter account or maybe a shared chat account. All right, and then finally for me, a few other areas here. Games is actually a great example. They're programs with either incomplete or asymmetrical information across the various participants. They often are transaction intensive, and they can be used to deliver rewards which people would want to be assured they would receive in a trustless fashion. So I'll let Brandon speak more about gaming, but that's a great use case. Attestation of model, actually, Jan did a great job for us explaining that earlier, so I won't go into detail, but you can potentially set up any computational program off-chain and have proof that it's been executed in the way you expected, with inputs you expected, with recency you expected, and that the output has not been tampered with. Oracles, many of these examples require inputs that are trusted, and or using ZKPs in oracles can help you to get data sets, mask some of it if it doesn't need to be disclosed, transform some of it if it can be disclosed in a way which is generalized, and save some of the privacy that's embedded in specificity. Credit scores, as I already said, is a great example. And then, bridges. I mean, the nil bridge, the Mina Ethereum mainnet bridge is a really interesting example. I think there's one other case of a chain following that now, and that could point to a way to make new forms of bridges or potentially add another layer of assurance on existing bridges. So I'll hand over to Brandon.
Hello. Cool. So my animations didn't make the transition into PDF, so excuse me. So everyone, please direct your eyes to the top left of this slide. So I want to first, I guess, just kind of at a high level, what I want to talk about is a new class of application that I don't think anyone's ever talked about, including me. So forgive me if it doesn't make sense. I hope it does. Which is possible with thinking about recursion in a specific way in ZK recursion. So first, let's look at the current landscape, right? So on the top left, we have normal on-chain computation in this is the landscape of computation with blockchains. So this is typical smart contract platforms, Solidity on EVM, whatever. If we go to the right, we see what I'm going to just call self-sovereign ZK. So an example of this are ZK apps on Mina, the smart contracts on Mina, which is where what we saw on the Aztec slides as well, where the first layer, either all of the proof or the first recursive layer of proof happens on the client side. And what's nice about this is your private data doesn't leak to any counterparty. So you can do cool stuff with privacy. Then at the bottom here, we have what I'm calling typical ZK rollups. And this is where I'm framing it this way to help motivate the next thing. So pay attention to this explanation. So it's where off of the main chain, maybe entirely off chain, maybe on a layer 2 or something, depending on the implementation, computation is sequenced by some counterparty, which is either some centralized service, it could be some other blockchain, and on Mina, this can show up we have very easy ways to build application specific rollups that can be run by some central service, or put on some kind of other blockchain or whatever. Okay, so this is the landscape as I see it, I guess. And then if you go to the next slide, Phil, there's this kind of use of recursion that I haven't seen anyone talk about, which is where we do the actual recursive like roll-up layer, so to say, in a self-sovereign manner with multiple parties. So recursive composition actually happens on the client side for whatever client means, I guess, in the user's custody on some server or whatever. And we're bouncing this recursive proof to different parties constantly and adding one recursive layer or combining two things at once. So if you go to the next slide, this is I'm going to present a cool multi-party self-sovereign recursion example to help get it into your brain. But I want it to be clear that like this is, it would be cool if like everyone started thinking about this as a class of applications to build, because I think there's a lot of really interesting things we could do. So before I do that, I'm just going to give like a little bit of background on Snarky.js, which is our programming environment. But I was, go ahead to the next slide, Phil. I was expecting to see more code actually in other talks, and I didn't. So maybe I'll just skim through this really fast because it's not really that important. But basically, smart contracts on Mina, we have state variables. This is our public state. You deploy a contract, and then you have methods, and methods have private inputs or the witness, which are arguments, and then your public input is given by the state. And then inside the method, you have updates and preconditions. The important thing that I want people to take away from this is you actually are writing a circuit. So there's no VM, typical VM with bytecode and things. You're actually writing a circuit because Mina's proof system is universal. Like you can deploy a circuit later and have it roll up into the main Mina circuit, even though it hasn't been declared yet at the start of the circuit. Anyway, okay. Could you just skip the next slide, Phil? Because we're running out of time. Cool. So poker is a game. You have cards in your hand. There's a deck. The private state is your hand. And when you draw a card, there's some kind of you need to make a proof that like you drew the card in a way that was fair and you didn't just make up the card. But replace poker with any sort of card game. So if you go to the next slide, if you can imagine like maybe the game gets set up by the player one or by someone else. Player one takes a turn, does this like one layer of recursion on this proof, and then passes the proof over to player two. The mechanism by which you pass the proof can vary depending on the trust assumptions you want to make in your application. But for now, just think about it like you're literally passing some binary data to another person. You're off chain. This is all off chain. Player two takes another turn, another layer of recursion, hands it off to player three. The game keeps going until it ends, or someone times out, and then only then it settles on chain. So what's cool about this, if you go to the next slide, is you're not limited by throughput. There's no kind of scalability problems because there's no centralization. Everything's generalized. Even the rolling up is decentralized. And you can generalize this to really any application. I just want to, there exists a space of interesting applications that people haven't thought about, I think, and it would be cool if people thought about them because there's really cool implications of this outside of just games. So yes, that's it.
Cool. So feel free to reach out to us. Brandon, my Twitter handles are down the bottom there. You can already start using Snarky.js to build ZK smart contracts. It's written with TypeScript libraries. I mean, the goal is to make it as intuitive and usable for developers out there who are not cryptography experts. So, it is definitely a different approach. And Brandon just pointed out some of the good things about it being a different approach. So it takes some learning, but the documents and the framework is already out there. There's also another example here of a recursive game mastermind, which we included in our launch material back in June. So that could be interesting also.
Cool. Thank you. Very nice talk. Thank you, Brandon. Thank you, Phil. We have some questions from the audience. We actually don't have that much time left. So we'll try to go through these questions somewhat quickly. The first one is from Guilty. He's asking, a game company has incentive to be fair among gamers, meaning ZK guaranteed info asymmetry itself doesn't mean to matter much in the eyes of gamers. What are your thoughts here?
Yeah, I have some thoughts. I think there's I'm going to use gambling as an example. So forgive me if your regime that you're a part of, frowns upon this or something. But there have been multiple cases of like hosted online poker companies, for example, just their staff like looking at the data on their servers and cheating and things. So I think there's cases where and also games where you're bringing like real world information about yourself into the game in some way, like via NFTs or some other kind of some form of identity that you want to mask in some way. So I think maybe it's not typical existing games. Maybe there's things where ZK doesn't really help much, but there's kind of a space of interesting types of games that and gambling and things like that where it could really help.
Yeah, I mean, the other thing I'd say is that, gaming is a great way to demonstrate the potential value and the use case of recursiveness in ZKPs and ZK snarks. But, I kind of, maybe feel a little bit bad about making this analogy, but, there's a lot of overlap topologically between gaming and financial services. And it could be that some of these techniques could also be used for things like, bilateral off-market trading. I mean, there's a micropayment rollups. There's a range of things that could use the patterns that are demonstrated by these games.
Cool. We have a few more questions. The next question is about ZK KYC and how it relates to mixers and other use cases. Could you talk a little bit about it?
Yeah, I mean, so it's pretty straightforward, and I think it's sort of somewhat overlapping with the identity case. I mean, you could construct a mixer that only accepted transactions in either direction from a wallet that had a non-transferable NFT, and the non-transferable NFT would designate that the wallet holder had been given that non-transferable NFT by a regulated institution, and the NFT said, we have maybe fully KYC'd them, we've maybe performed some kind of checks that have indicated that they're not violators of OFAC regulations. It's easy to say that. I mean, the reality is that some of the banking regulations, and it varies by country, but some of the banking regulations are very, very particular in their implementation. And so, for example, in the past, it's not been possible for banks to either practically in terms of liability, or in some cases explicitly in terms of regulations, to delegate KYC responsibilities to each other. So I'm not saying it's like an easy fix, because you do have to navigate around issues like that. But certainly in principle, you could have a gated on-chain mixer that only allowed people with certain designations to use it. As I said earlier, it does then run into the issue that mixers rely on transaction volume, and so the more that you're gating it, the more you're going to have to build up additional transaction volume to prevent people from correlating inputs and outputs.
Mm-hmm. Cool. Yeah, we do have more questions, but we are kind of out of time. We had a plan to have like a 10-minute panel at the end of the session, but there's hardly any time left for it. Could you go to the next slide, please? Right. Maybe next question. Oh, this question is fine. So maybe in the last few minutes left, we can quickly sort of see what people have to say about this question outside of the blockchain context. Could you speak a little bit about how the ability to prove correctness of computation could be useful? Anyone?
So I'm actually quite excited about what Ferdinand was proposing, and there's already some like open source code for building like very simple linear models that you can call machine learning. I think this is important because with like larger and larger models, people will care about like what data that model was actually trained on, and whether the one that they are running is the same that the company who actually like trained the model like produced. And of course, the company also doesn't want to reveal the parameters of this model. And if there's a way to do this that guarantees them the freedom to not reveal the parameters while giving the ability to use this model, then that's great. Of course, there are like huge costs to proving large models.
Right.
Yeah, I'll jump in. I think that the one way to think about this is what computations only make sense, like where does ZK only make sense in the blockchain? Because I think a lot of the things that we're doing with ZK don't have to be on a blockchain, so I think like computation, a lot of computation could exist outside the blockchain. The real thing that a blockchain gives you, at least Mina's blockchain, is or really, I guess any blockchain. One thing is composability. So you can rely on another program and another service and like be confident that it's doing what you expect. And the other thing is your users, at least for Mina, your users can rely that like when they're interacting with a program that they don't have to trust the like executor of that like the program is sort of correctly implemented. Like they know that the source code, the proof that they've submitted, verifies against the source code that they expect. And I think for even for like the ZK machine learning example, you have to trust that someone has run the program on like the specific circuit, unless you get to see the circuit and execute it yourself. Or I guess there's like a lot of, in my mind, there's a lot of kind of back and forth you need to do to communicate like exactly how something is running that like a blockchain kind of gives you. But if you're okay making those trust assumptions, then you don't need a blockchain. Was that coherent? I don't know.
No worries. I would actually love to talk more about this, but we are kind of out of time. It's 10:30 already. So let's go to the end of the presentation. One thing I would like to point out is that we have an incubator we're planning to launch, and we'll be accepting 3 projects this year. If you're interested, you can apply at that link. And that's it. Like, thank you to all the speakers. Thank you for everyone who attended, for all the great questions, great answers, and hope to see you next time. Thank you.
Thank you all.
Thanks
For having us.
Thank you. Bye.
Thanks for organizing.